Hello everyone, I'm Junhong. I'm glad to share our work RS2G, data-driven scene graph extraction and embedding for robust autonomous perception and scenario understanding. Our work focuses on one of the most important tasks in autonomous driving, subject risk assessment. It is the task that led the car to determine whether its surrounding is dangerous or safe, and then it can do the corresponding action. And our goal is to make the autonomous driving more interpretable because unlike human, we can easily to know the relation between us. For example, the car is in front of us, or there's some important item like human or dogs or something else that need to give our more attention. And effectively modeling the relation among the road users is very important autonomous vehicle to understanding the surrounding environment. And our goal is to make a relation graph. And in the traditional methods, the car will use some fixed rule, like it is in front left of us or it is very close. And then the car can be extracted as node, and we can use this fixed rule to build the relation graph like this. And our model is a data-driven model. So unlike the fixed rule, we will push the model to learn the rule by itself. And the object like car will be extracted to the node and then use a node encoder to get its feature. Each row represents an object and each column is its feature. And then we can let the model to learn the relation by itself. It can be more expressive and more efficiency, which we will be discussed in the latter part. And our workflow is very understandable. First, the sensor will get sensor data, and we will use some CNN-based object detection like RCN to get object of each object. And then we will extract this object into a node, and each node will extract their feature by a node encoder, and then we have the abstract expression of the node. And here we use the transformer encoder as our relation generator because the attention mechanism it is very useful in this part, but only in the NLP or computer vision everywhere. And then we can build our scene graph, and this is our data-driven scene graph extraction part. Next, this scene graph will be used to the downstream task. We divided our model to the spatial model and temporal model. And the first part is the spatial model. It will use the graph convolution. Here we use MRGCN to do the graph convolution. And after this graph region pooling, and then we get a requirement for our temporal model. The LSTM encoder will use the output from the spatial model and then to make the prediction, and then we use MLP to get our final output, whether the surrounding is safe or dangerous. And then we finish our risk assessment task. And the algorithm can be simulated as the future code. An object and their attribute D will be put into our function. And we will first encode our node by a node encoder. And then we will use this node. Each node will get the relation with other node. And then we use the encoder we use the transformer as the relation generator to get the output, and we will define the number of the rules to restrict the rule to avoid overfitting, and then we get our final output, the scene graph. And an experiment can review our efficiency. For example, the first one in the left is the subject risk assessment. You can see from Bob in the 271 color, 1043 color, and 1361 Honda, the RS2G, our method, and outperform than any other methods. And 62 dash is also, and you may find very confused that why the 2D MLP things also work well. So why we will use transformer? And then we will explain that. And the second task is transfer learning. That's because for the 271 color and the 1043 color, they are the simulated data. And what we want to improve is their performance in the real world scenario. So we do the experiment on this. The simulation data is easy to get, easy to generate. So we will train our model in the simulation data and then to test their performance on the real world data. And it shows that the transformer RS2G has a much higher performance than the 2D MLP. And we do some evaluation study and analysis to prove its effectiveness. Here, we use the KL divergence to improve our transformer. The KL divergence is a technique that can let the relation more general. It is kind of a mathematical way to do so. And it shows that if we employ EKL divergence to the MLP RS2G, the performance will drop. However, if we use the KL divergence to the transformer, the performance will improve. So it shows that the transformer real encoder have a really good ability to generate the relation, and even the relation they generated are more complex. We need to use some methods to make it more generalized. And however, the MLP uh, has a weak ability to do so. And besides the encoder part, we also focus on the downstream component analysis, and we compare the rule-based method with our RS2G method. It shows that in the rule-based method, the MRGCM plus the LSTM will have a better performance. However, if we use the data-driven part, that is the transformer here encoder, the best combination is MRGCN plus the mean. Yeah, just the mean. The performance is the best and much higher than the rule-based method. It can also show that the rules learned by the RS2G, the data-driven methods, can extract some further information behind the ball. And that's why if you use some more complex model like LSTM, it will make its performance drop because the relation they learn can have the enough information for they to prove. If you use LSTM, there may cause some overfitting, but the rule-based method, there are no enough information behind the relation. So we need to use some complex model to make it better. And at the last, we also compare with our methods to the rule-based methods. This is a heat graph. Each number here represent the cosine similarity. And we discuss three parts of this. Each column in the here is the relation generated by the rule-based. We will use the data-driven relation to do the cosine similarity to see if it can somehow to be explained by the rule-based method, and we can find out some relation generated by data-driven is like is in kind of the direction, because direction is one of the most important relation we need to judge when we do the subject risk assessment. So the data-driven relation can generate some relation that can be widely used in each rule. And besides, there also are some transfer learning ability we can learn from that, because like the relation 7 and 9, that the relation of this and this is kind of larger than the other one. So it shows that our methods can find the relation that is maybe more important somehow. Besides, it can also learn some multiple rule-based relation, because for the rule-based methods, it's kind of can be expressed as a one-hot encoding. If we define its in relation, then it should be 1000000. However, the data-driven methods can combine or fuse many relations of the rule-based methods. So it can have a higher performance, higher information, and higher interoperability, which can significantly improve the model performance. And that's all. Thank you. We are from the UCI AICPS lab.